back to a new video. Today's topic is about recursive backtracking. A pattern to solve various types of problems, whether they are decision problems, asking us if a solution exists or not, search problems, whether they are asking us to find a real solution, or optimization problems, they are asking us to find the best cost of a solution and the best cost to come up with a solution. Recursive backtracking is a design strategy stemming from brute force algorithms, where you have to discover all possible solutions until coming up with a solution to the problems. It utilizes this using recursion. The following diagram represents decision trees for recursive backtracking problems, where these represent the states of the program and the arrows represent the transitions between these states. Let's say you launch your program and now you are initially stated at this state. You have three choices to make in order to solve the problem. You don't know the solution at which state exists. Let's say you go down this path. Now you are in this state. Then let's say you also went to this state in order to discover the solution. Once you are here, you realize that the solution does not reside in this path. What can you do? You backtrack to the previous state. This is the process of backtracking, that you can go back to the previous states and discover new paths in order to find the solution for your problem. So what is the difference between normal recursion and recursive backtracking? In normal recursion, there is a recursive step and a base case, where once you solve the base case, you go back with recursive calls and solve the sub-problems in order to solve the main problem. However, in recursive backtracking, you can always go back and forth between two different states in order to discover a certain problem. An example on both recursion and recursive backtracking is the following. Imagine you want to generate a permutation of a specific sequence of numbers. Let's say 1, 2, 3. You want to get all the possible orderings of these numbers. For example, 1, 2, 3, 1, 3, 2, 2, 1, 3, etc. You can utilize this and solve this problem using recursive backtracking. We shall discover the solution at the end of the video. Example for normal recursion is Fibonacci sequence, where each two numbers is the sum of the next number. For example, 0, 1 sums to 1, 1, 1 sums to 2, 2, 3 sums to 5, and etc. You can solve this using the recursion. So in normal recursion, these are the two cases that we can have. A base case representing the termination of the program, and a recursive case that calls previous sub-problems in order to solve. Here in Fibonacci sequence, the base case is when n equals to 0 or n equals to 1. We return 0 and 1. However, if we are at a recursive case, let's say 5, we want to know f of n minus 1 plus f of n minus 2, which is 2 and 3, and so on. However, in the generate permutations problem and in any recursive backtracking problem, these are the three cases. We have also a base case, a recursive case. However, we also have a backtracking where we can go back to previous states and discover possible solutions for the problem we have. So guys, let's now solve the permutations problem. As you can see, here is the decision tree for the permutations problem. I took 1, 2, 3 as a test case to generate it, but you can take any test case you want. For example, 1, 2, 3, 4, 1, 2, 3, 4, 5. Here, how can we know the states we have? We have three numbers, 1, 2, and 3, right? So the permutation we have, the ordering we have, may start with either 1, either 2, or either 3. If we have four numbers, let's say 1, 2, 3, 4, it can start with either 1, either 2, either 3, either 4. So the choices we have here are based on that. Here are the numbers that start with 1, here are the 2, and here are the 3. Let's say we picked 1 to start with. Our choice is 1. So we move to this state. We put 1 here, and what are we left with? We are left to pick from 2 and 3. So we have two choices to make. Let's say we picked 2. So we are here. we still have 3 to pick from, and only 3. So we picked 3 because it's the only number left. Now we have 1, 2, and 3. There are no numbers to pick from, so we backtrack, right? This is the base case. As you can see, when the number becomes, there are no numbers to pick from, that is when the base case is reached and we can backtrack. Now let's say here, previously I made the choice to pick 2, now I want to pick 3. So I picked 3. What am I left with? I'm left with 2, right? So here, the same process repeats, and I have 1, 3, and 2. This is a base case, so I backtrack, and backtrack until reaching the state here. There are no choices of 2, 1, then there are 2. I choose 2 now as my next choice. Here, what am I left with is 1 and 3. So, if I pick 1, then 3 is left. So I have 2, 1, and 3 to pick from. The same process repeats until picking 2, 1, and 3. Here's a base case, so I backtrack until reaching here. Now I don't want to pick 1, so I pick 3. So here I have 2, 3. What am I left with? With 1, so I pick 1, 2, 3, and 1. Then I backtrack until reaching 3. A lot of backtracking in this video. So the same process repeats until the subtree of 3. Now let's see how the code for this decision tree actually looks like. And after that, we shall see how the code actually works by simulating a test case on the code itself.
So guys, here is the question for the permutations. As you can see, given an array of noms, we should return all the orderings of the noms. How shall we approach this problem? First, let's create a result that should hold all the cases we should have. It should be a 2D vector. Now we need to initialize another function that should add the nums, and the so far the nums represent the choices we should pick from, and the so far is what we picked so far. So it should be first void. First, what is the base case? The base case, as you can see, or as we discussed, is when the nums, the size of the nums becomes 0. There are no choices to pick from. So if nums.size becomes 0, we first add to the result the so far. If it's not a base case, then we for loop on all the choices and pick a choice at a time. So for integer I range I less than nums.size plus I, we pick a choice. So far dot pushback nums of I, and now we add all the choices we didn't pick, so we can pick them in the next recursive call. So first, let us initialize a vector, iterate over the numbers. If I doesn't equals to j, then we add a number to the next, meaning here I that we added it is different than the numbers we add, so we don't want to add the same number we picked into the next. So next dot pushback nums of j. Once we added the next, then we recursively call the next iteration to pick from. The next becomes the new nums, and the so far remains to be added as follows. So here becomes next, and so far. This can be without this. When we finish backtracking and we return to the previous state, as we saw, we should remove the last element and take the next choice. For example, if we pick 2 in one choice, we should remove 2 and pick 3 in the next choice. So we remove the choice that we have taken so far. For dot pop back. This should be it for the backtracking. Now we should here initialize a vector for so far. Call the backtrack, return the result. Can run. So guys, as you can see, let's run the problem. And it's accepted. Let's submit it. And as you can see, it's accepted.
Now after viewing the code, let's simulate the test case 1 to 3 on the code. First, at the first iteration, we have nums equal 1 to 3. So far becomes 1 because we are iterating I equals to 0. And the next are all the numbers except 1. I call a recursive call to the next number. The next becomes the new nums. So far becomes 1 and 2 because I is 0, and the next becomes 3 because all the numbers except 2. So the next now becomes the new nums. As you can see, the nums becomes 3. I now is 0, so I only pick 3. So far becomes 1 to 3, and the next is empty. Here you can see that the next recursive call will be the base case. As you can see, nums now becomes empty. So far is 1 to 3. So the first thing to add up is 1 to 3. Now this scope is finished, so we backtrack. Here I is 0, so we continue the for loop, but it's an array of single element, so it finishes and it backtracks after popping 3. Now here it should continue after popping 2. I becomes 1, so it's here. So far becomes 1, what it was before was 3. And the next is all the numbers that we didn't pick, so 2. This also calls another call. So the next thing to add is 132. Now it also backtracks, reaching this scope. Now I was 1, so it's 0, 1. So it has finished the for loop. It pops 3 out, and it calls back the previous scope because it has finished, the for loop has finished iterating. We are here, so we pop 1, erase next. Now I becomes 1, so it's pointing at 2, so we add 2. The next becomes 1 and 3, and we call the next scope. So far is 2. So now I is at 0, so we add 1. The next is 3. We call the same procedure. Now here the I becomes 2, so the next I will be 3, but it's 0, 1, 2 here, so that program will terminate. As you can see, using backtracking we have managed to generate all the permutations of 1 to 3 which are here.